today it's my pleasure to introduce Claudia Cenedese. Claudia is a senior scientist in physical oceanography at the Hudsall Oceanographic Institution. She's also an adjunct associate professor at the College of Engineering at the University of Canterbury in New Zealand. And she is a faculty of the Geophysical Fluid Dynamics Summer School, as well as a fellow of the American Physical Society. She's been involved in a number of oceanographic research cruises, both in Antarctic and in equatorial waters. And the focus of her research is to improve our physical understanding of how mesoscale and sub-mesoscale processes, such as buoyant plumes generated by melting glaciers and iceberg, influence the general circulations of the ocean. And her goal is to improve the representation of these processes in ocean and climate models. Today, she's going to talk about how icebergs melt. So over to you, Claudia.
Okay. So thank you, Adrian, for and Steve for introducing me and inviting me to give this talk. So today I'll tell you everything I know about iceberg and also the things I don't know and that we should try to get to learn. So this is not work I've done by myself, but with a lot of collaborators, which are listed down here. And especially I want to point out Fiamma Stranio, that is my good friend and also collaborator that brought me to Greenland, actually a couple of summers, before COVID in 2018, where we kind of did surveys of iceberg. And this is a picture we took of an iceberg that we named Cervino, because from far away, they look like the mountains that we have in Italy. That's called Cervino, the Matterhorn. And I'll show you some of the data that we acquired during this cruise. But let's start on why do we care about icebergs? Well, we all know that the ice sheets are melting fast, that the ice sheets are, the glacier accelerating, the sheets are receding. And of all the amount that is discharged of the total freshwater flux, both in terms of liquid and solid form, there's discharge into the ocean by the two ice sheets of the Greenland and Antarctica. Half is in the form of icebergs. So it's very important to understand how these icebergs, first of all, move, which path and trajectory they follow, and also how they melt, because by melting, they can add freshwater flux to the water column, so they change the stratification. They can influence the sea ice formation. Some models suggest that iceberg melt can increase actually sea ice formation, and so reduction of albedo and kind of a negative feedback on climate. And also they distribute nutrients and carbon as they melt. And they can influence, obviously, the circulation, like the meridional overturning circulation when they melt in the Labrador Sea, because they prevent deep water. The fresh water can prevent deep water convection. So this picture on the left shows you Greenland, the Greenland ice sheet, and the color represents velocity of the ice sheets, and the purple up. Do you see my cursor?
Yes, we see.
Okay. So I'm going to use that. So you see this purple spot are the highest velocity, and this is the location of what we call marine terminating glaciers. So a glacier that terminates in a fjord. And so it shows that they're all pretty much accelerated in Greenland. And in the Greenland mass loss to the ocean is this kind of cyan line, which actually is even more than Antarctica these days. But half of these, you have to remember, basically that is iceberg. So let's see how iceberg behave. First of all, how do they form? This is a nice picture sketch that was in he and Hewitt review paper a couple of years ago, where shows that you can have two different kind of ice sheets ending into the ocean. So we have on the right, what we expect usually is in Antarctica, that you have this large marine sheet where and long floating ice tongues, they're called, this where the ice sheet is afloat. And so the stresses far away from the grounding line, which is this point here where the ice detaches from the bottom, are pretty small. And so the ice fracture much more farther apart in terms of length scale. So you get bigger chunk of ice, bigger icebergs, and also much more rarely. So in Antarctica, you form what we call the tabular icebergs. So there are those large icebergs. While in Greenland, because this ice tongue, basically, they have been broken up already. There's only one left, I think, 49 north. What happened is that the glacier or the ice streams are narrower, and so the stresses at the end are much higher, and the ice is much more crevassed, and it calves very frequently, generating kind of smaller icebergs than in Antarctica. And another thing I want to pay attention from the sketch is that it's really important where did this iceberg then float? Usually, say in Greenland, we have fresher and colder water on the top and saltier and warmer water at the bottom. But that is very important, the stratification and also the velocity structure and vertical profile where icebergs are embedded in. So these are pictures of this large tabular iceberg, like the Iceberg B15 that was formed a few years ago near the Ross Ice Shelf, and these instead are smaller iceberg in Greenland. And what characterizes one or the other is the aspect ratio, as you probably guessed. And here I'm just defining L, capital L, as the length of the iceberg in the direction, in this case, when they are tabular, usually we choose the longest one. D is the draft, so it's the amount of ice underneath the free surface, and small h is the freeboard, so it's the amount of iceberg on top of the free surface. So large tabular iceberg have very large aspect ratio, while this Greenland iceberg have small aspect ratio. So that's how you distinguish the two. And they have fairly different dynamics too. So we'll see that as we get along on the talk. And this is a picture of Malik Fjord, where I went on my cruise a couple of years ago. I started from down here. We went all the way around here into this passage and then into the fjord is here. And you can see this fjord is located in Southeast Greenland, and you can see the glacier terminating up here. There's a lot of melange near the glacier. Basically, it's a bunch of iceberg just cramped together, and then they kind of float around. So there are some big ones that you can see even from up here, and some small ones. And we survey some of those. And we can only do this in the summer, because in the winter, you can see here, everything is basically, there's either sea ice or it can be broken up sea ice. So these are not necessarily icebergs. In fact, they're not icebergs, they're just sea ice that is broken up. So you cannot go there in the winter. So it's very hard to observe iceberg in winter. Okay, so let's start understanding first, how do an iceberg move? You can write the whole momentum equation, and we're going to, if the iceberg are big enough that feel influence of rotation, their acceleration is influenced by the Coriolis force. Obviously, the part outside of the iceberg is influenced by the air. So there's some air stress, ocean stress. There could be some sea ice stress if there is sea ice in the winter, for example, wave radiations and pressure gradient. But we're going to make a very simple model in which we assume the iceberg is in steady state. It's small enough that rotation is not important, and there is no sea ice or waves or no pressure gradient. So you can just balance the stress in the air versus with the stress in the ocean. And we're going to compare this simple model with some data. So what we had in the fjord, again, this is another picture of the fjord, we had an instrument that's called PICE, which is a sensor-equipped invert echo sounder. So it sends pings, and when there is, the pings return when there is a strong reflector. So that could be either the surface of the water, which we cannot know what it is up here, or can be when an iceberg goes inside the cone of captures this pi signal. And when the iceberg goes through, then these are the pings back of the echo sounder. And don't think that this is the shape of the iceberg. This is just where the pings come back in time. And I'll show you better in the next slides what those parabolas are. And also next to it, which is very important too, we have an ADCP. So we had the velocity of the ambient fluid, which here is depicted in kind of blue, that is negative, it's going in one direction, and kind of reddish in the other. So you can see already here that this iceberg seems to be embedded just mainly in the top layer, but on the bottom layer, that is going in one direction, but the bottom layer is going in the opposite direction. So if we had a longer and deeper iceberg, that will feel the influence of both layers. So this is a little movie that should have started, but I'll repeat it. So it's a little toy model that actually Anna that did this work do. So this is our iceberg going into the cone, as you can see down here, of the instrument. And so every time the iceberg goes by, it makes a cross. So you see the iceberg didn't go exactly over it. So when we measure the draft, this lower point here, there is it's 180 meters, and that could be, there is a range, because depends if we don't know usually if the iceberg went exactly on top or on the side, but that gives us the range of draft that we can measure with this method. And actually the curvature of this parabola gives us the velocity, because that tells us, where the iceberg was compared to the previous position. So we can determine the velocity by the curvature of this parabola, and the draft or range of draft by the maximum depth of this parabola. So once you know that, you can compare that velocity that I talked before. You need to do some assumption about the shape of the iceberg, and I'm not going to do that, but the model, that 1D model versus the observation for other, if you assume that the iceberg is a cube or a cone, they fit pretty well. In that, we had a data set with 90 icebergs. And in particular, if you compare this measured velocity with either the depth integrated ocean velocity, so that will tell you what is the influence of what we call the stress due to the ocean. This is comparing that velocity with the wind speed, along fjord wind speed. So that gives you an idea of the stress due to the air. And this is just the draft. And you can see there is the highest, the data only correlated with the ocean velocity. So that, as you expect, iceberg are influenced by the depth average velocity in the fjord. And although I would say this audience is pretty obvious, a lot of parameterization that I use today, and to this date, they only use the surface velocity of the iceberg, not the depth integrated. But for both is a surface velocity, not of the iceberg, of the ambient water, not the depth integrated, both for the calculating the drift and the melt. And I'm going to show you in a second why that is not going to work well. Because these are a selection of 6 icebergs, where the iceberg is represented by these blue lines, and the displacement from the dashed line is the velocity of the iceberg. So the draft is, how long is this line, and the velocity is the, this distance between 0, the dashed line and the blue line. Then this black line is the velocity of the ambient fluid. So that's the ADCP velocity. Up here, there is a wind velocity that has been scaled by a factor of 5. And so you can see that, for example, in this sample of iceberg, there are some cases in which the iceberg is fully immersed in a layer that has a fairly homogeneous velocity. So it's going to move with that velocity. And this is one example. But other times, here we have an iceberg that is basically in a shear layer. So taking the surface velocity will not give you the right velocity. And this is another example up here and up here. And so in these cases, you really want to know the whole profile of velocity all the way through until, for the entire draft of the iceberg. Otherwise, you're going to predict, incorrect velocity of the iceberg. And finally, you can have, Anna quantified actually this error that you can make if you use the surface velocity or this average, this depth integrated velocity that gives you the velocity of the speed and the iceberg, and you can make an error up to 60% if you use the surface velocity. And also, although I haven't talked about melting yet, but a lot of melt parameterization use velocity. Again, if you use the surface velocity instead of the depth integrated, then you can have an error on the melt too of 70%. So now let's look at the melt rates. So we learn how we form this iceberg, and we learn how they move. Now let's see how they kind of get destroyed. So there are different processes that can deteriorate an iceberg, and they're kind of all but one are depicted in this kind of schematic. So we can have an iceberg that we said can be in an ocean current, and then it can have its own velocity. Again, if there is shear, the velocity of the iceberg can be different from the one of the ocean current. We know that there's going to be some surface melting. And then we can have what is called basal melting, or also forced convection. And then we have some side convection, or what is in the literature called buoyant vertical convection. And then we have the melting due to the wave erosion. Now, I've followed here just the nomenclature that has been in the literature, but we'll see that it doesn't quite make sense sometimes, because what about basal melting? What's the base of an iceberg like this? It makes more sense when you talk about a tabular iceberg maybe, but bear with me. They're just different physical processes, and then we'll see that then we'll choose just some to be the most representative. And another thing I want to clarify is that when I talked about melt rate, is a rate, so it's a velocity. So I'm going to express in meters per day. And that is the velocity at which the ice interface recedes in the system of reference of the iceberg. And if you want to calculate the volume, then you have to multiply that velocity by the surface area that has that melt rate. So the melt rate is expressed as a velocity. So these are the parameterizations. So we'll go slowly through that. So there is a forced convection that it was the base melting. That is basically is a parameterization that was derived thinking about heat transferred from a hot plate. So if you think about, again, a tabular iceberg and some fluid going, like that, for whatever reason, the iceberg has a different velocity than the ambient, and then there is fluid going, ambient water going at the base, then you can think, okay, that process of heat transfer is very similar to having a hot plate and a uniform flow that goes through it. And so I can go into all the details, but they were worked out in the past. And so this is the parameterization for this bottom basal melt rate. So it depends on the velocity, on the relative velocity of the iceberg to the ambient. So everything that doesn't have any pedics, like U and T, is the iceberg velocity or temperature. Everything with an O is the ocean, so it's the ambient. So this is the relative velocity of the iceberg to the ambient flow, relative temperature. This is the length of the iceberg, and kappa is a variable that basically depends on the Prandtl number, on the thermal conductivity, viscosity, latent, or basically all the thermodynamics is here. And it has different value depending if you're looking at an ocean, which has a temperature of 0 degrees, or are you in the lab, for example, doing an experiment at 20 degrees. So you can use this parameterization both in the ocean and the lab. And usual parameterized value, maximum parameterized value of this melting are order of 1 meter per day. Then the vertical convection instead, some people parameterize it just to be independent of velocity. And the parameterization is an empirical fit basically to some data of iceberg melting in different temperature that they were done in the 80s. And this is the expression. And this value, this contribution to the total melt rate usually is pretty small. Again, a quarter of what a fifth of what we had before. So usually this contribution is neglected because it's much smaller than this one. But obviously, it depends also on the aspect ratio. And then we have wave erosion. And what waves do, they erode the ice and they make a little notch in the ice. And the rate of melt is basically influenced by the sea state. So how big are the waves, which is this S sub S. The ice concentration, this IC, because if you have sea ice, you dump the waves. So, that given the same wind, if you have sea ice or not, you'll have a different wave height. And then depends on the temperature of the surface, this T sub S. And so this is, again, another empirical parameterization, which takes into account these processes. And this term is big. It's as big as the forced convection terms. It's between 0.5 and 1 per day. The interesting things are that these waves, what they do, they form this notch. And so what I kind of represented up here by this yellow little birdie beak that is kind of dropping, you can form this notch, and then this ice on top doesn't have any more sustain. So that's how it breaks. And so you can form much smaller iceberg. And so I'm going to show you a video that has some sound, so be aware, don't jump up or you'll wake up, where we actually almost, we're very close to something like that happen. So the scream is because we were here taking measurements just few seconds, few 10 minutes before this happened. But you can see this all part of this big iceberg kind of collapse. And the reason is because there was, again, wave erosion. And you can see this lightest water underneath. What remains is this foot of the iceberg. And you might have seen picture of iceberg from the top, and you see this very light blue kind of bigger outline. And that is what is called the foot of an iceberg, which I depicted like in this. And then there's another way to deteriorate an iceberg beside this collapse of the top part is called the footloose mechanism that was introduced by Till Wagner a few years ago, and it was also known before. But basically what happened is that you have this foot of the iceberg going out, and if this foot is longer than a certain critical value that I figured out analytically, then there is a torque, that this foot is buoyant, so you want to come up, so you have a torque, and that creates a stress that can break the iceberg in pieces. They're called child iceberg. They have a length scale at LC that usually is much longer than LF, especially for tabular iceberg. And this is a mechanism that basically contributes for 80% of the decay of large tabular iceberg. So we're not looking to this, but this is a way that basically you can have how these big tabular iceberg deteriorate. They break into smaller iceberg and smaller, and then eventually they have more surface area where to melt, and they can travel in different way than a big one. Okay, so now let's see. So now we kind of know how they move and kind of how they melt, although again, these parameterization are very empirical. So let's have a look now. And that's basically what I've done in the past 10, 15 years, is to look at what can influence this melt rate. So one thing that wasn't very satisfactory to me was that parameterization of Wicks and Campbell, that for the basal melt, or this force convection, that takes into account velocity. Because I've done a lot of work with Glacier too, and I know that even if there is not advection, you can still melt, because you can form these plumes and that they rise alongside the glacier. So I said, okay, I have an iceberg. It's a bit different. Let's assume that my iceberg is in a two-layer flow. So let's do it simple first. And this flow is sheared, right? So if the velocity of my plumes going up, my meltwater plumes, are much larger than the velocity of the ambient fluid, my plumes are not going to care about what's going on in the ambient, and they keep basically going up, maybe a bit more mixed, but not much changes. And so I'm expecting to have an intrusion at the interface and one at the surface. And as probably everybody knows, that dumped at least in the fluid tea room, there's a beautiful picture that Herpert and Turner did, experiment actually in stratified fluid. And when you put an iceberg instead in a stratified, an ice block in a stratified tank, you have all this intrusion coming in at different layers. So this is just when you have two layers, obviously, but let's keep it simple and forget stratification for now. However, if the velocity of the ambient fluid gets much stronger, is much larger than that of the vertical plume, you can imagine that this plume will be swept downstream, and they wouldn't be attached to the wall anymore. And then the heat transfer will be, instead that through the entrainment of the plume, will be directly from advection. So this was my idea before starting this project. And indeed, this is what we observed in the lab. So we went to the lab. Again, very simple. We start with very simple, just one layer, one density, and one velocity. We put an ice block inside. So we weighed it first. With an ice block, we weighed it. And then we put inside a tank at a fixed location. So there is a relative velocity, because the ambient fluid has a velocity u and the ice block has a velocity 0. And then we made the experiment run for 10 minutes, and then we weighed the ice block again. And that's how we calculate the melt rate. And what we observe is this. So this is what happened when there is no velocity, 0 velocity. So you put this ice cube there, and you see the plumes going up. This is like what I observed for the glacier, most of the melt water is accumulated on the surface. This is, again, it's not pure melt water because there is entrainment of ambient fluid in these turbulent plumes. So obviously it's warm water getting close to the ice. That's why it melts. And then you can see this double, diffusion process that the water is, the warm water is getting colder. So it's kind of sinking and then bringing some of the blue dyed water down too, but most of the water goes on the surface. Now, if instead you put this in a uniform flow with a velocity of 3 centimeters per second, things change very dramatically, because we don't see any dark blue accumulation of dye on the surface. We don't observe any plume. And so we think that this means that the plume have been swept downstream, and the meltwater is mixed all the way in the layer of the draft of the iceberg. So it's much more diluted and it reaches a deeper depth. So this is very different. Let's see now how instead the melting differs, if any. So this is the distribution of melt water that we could observe. So this is the plotting SMR is what we call submarine melt. Submarine melt rate. So this is again, it's a velocity and indicates the melting. And these 3 ABC represent kind of 3 regimes, although I'll focus mainly on 2. One, what I said, the plume attached for low velocity, or the plume detached, which they show a pretty sharp transition around 2.5, which is roughly the velocity of those vertical plumes. So that schematic that I showed at the beginning is indeed was happening in the lab. And then if you want to plot the parameterization that we saw before, that Wicks and Campbell, is this line that proceeds all the way down here, right? Because remember that parameterization at U minus U naught. So when U minus U naught is 0, there's 0 melting according to that. But there are the plumes. So instead, we propose a new parameterization that I'm going to show you in the next slide. And this is the black line, which we didn't have to fit. The only things we had to choose is the ice temperature, which was minus 15. We put what it was. And we put that kappa, that constant that includes the Prandtl number and all the thermodynamics that we put at 0.58, that is calculated for a lab experiment at 20 degrees C. So this is the new parameterization. So we decided if there are the plumes, so when this velocity of relative velocity is less than the vertical velocity of the plume, then we adapt the parameterization that we saw before, putting the relevant scales. So my velocity is not going to be my relative velocity anymore. It's going to be my plume velocity. And my length scale is going to be the depth of the draft of my iceberg, right? Because that's the, that will be my plate kind of things. Now it's in a vertical direction. And the temperature difference is the one between the plume temperature and the ambient temperature. Instead, when the velocity is large enough to sweep off the plumes, then we recover or use the same parameterization as below. And so you can see that this new modified parameterization takes into account melting that occurs even when there is no relative velocity, because the plume do the work, because the plume can entrain water in them and hence melt iceberg as well as the melt glaciers. So this is was a very good result that Anna Fitzmaurice proposed. And then when we look at the profile that she, the data that she collected in Malik Fjord, you can see that there are some cases, as I showed before, in which the relative velocity of the iceberg is very small. So in these cases where there is yellow, basically we expect the plume to be attached. And that happens in the 90 iceberg data set, kind of 40% of the time. And the melt rate is kind of double in that case. So that is an important factor that cannot be neglected. And so when you use this new parameterization compared to the old one, you get to average value of melt rate in this fjord that they kind of closer to indirect observation that were done using satellite images compared to the previous parameterization. But I don't know, these measurements might not be, they have the error bar too, but I feel like they are more consistent and physically based parameterization, because again, things melt even when there is no relative velocity. So this is the effect of ambient velocity on the parameterization, on the ice melting. Let's look at another factor. Do tabular iceberg melt as much as little iceberg like that we found in Greenland? So that's the aspect ratio melt. And this is work that a GFD fellow, Eric, at the time, Eric Esther did when, a few summers ago. So this is the experiment that he did. So in the same tank as we did before the experiment I show you, they had an aspect ratio roughly 1. They were, 10 and 15. It was the height and the draft and the length. In this case, instead, he made an iceberg that had very different aspect ratio. And he put them again in a velocity in the flume. So there is a relative velocity. And again, they are in constant ambient density. And the velocity is constant too. The upstream velocity is constant too. And so you can see the evolution in time of this iceberg, which was kept again 10 minutes in the tank and then waited before and after to calculate the melt rate. And you can see already how when you have a long, a high aspect ratio iceberg, something funny is happening because there is kind of this little dip here. It's pretty constant, the bottom surface is pretty flat downstream, but there's this little kind of dip. And even here, when it's small, you observe that it melts more in the back of the iceberg instead in the front. So why is that? So if you took the final side profile, so when Eric took away the iceberg out, he took pictures and then he determined exact profile compared to the original. So the original iceberg size would be the whole box up to here until, either 10, 15, 20, 25, or 30 centimeters. You use different length. And you can see that the final profiles, they both eroded a lot in the front, but also in the bottom. So this ice kind of shrinked in both directions. And but what is interesting to see that regardless how long the of the aspect ratio, the profile is pretty similar. It's just that it's melting up to a point. So when we had a small aspect ratio iceberg, we saw that it was melting more in the back, but it's actually the same thing as if you overimpose it as the little notch that we observe for longer iceberg. And these are the results for the highest velocity that we use, the middle, and this is not velocity when the bottom is totally flat. So that was interesting. That was this non-homogeneous melting on the bottom. And then before I kind of try to explain you tell you why that is, let's compare this melting with the parameterization that I showed you before. Let's see if they take into account this. And so these are the same profile in colors, and in the reds, there are all these different parameterization. One is the Wickham-Campbell, the dashed line, which for high velocity is the same as the Fitzmaurice model because they follow the same line. And the dotted line is another parameterization that's used a lot for glacier melting. This the 3-equation model of Jenkins and Holland. We takes into account the equation for salinity, temperature conservation, and then the freezing points of water. But as you can see, all these 3 parameterization, and the black line is the average, melt rate if you redistribute it just to have a rectangle. All the parameterization highly underestimate the melting of the ice, even the Fitzmaurice that we kind of try to take into account of this side plume. But there's something more here dynamically going on. So I'm going to show you first an experiment here where we put some potassium permanganate in front. So you can see this is going pretty fast because it's been accelerated, but you can see this blob of dark fluid, which is the meltwater because the iceberg is dyed blue, is kind of staying here, while the ambient fluid, every once in a while I see these red streaks, which are potassium permanganate, goes around and then kind of forms you can see like eddies and turbulence back here. So we thought, okay, this is very similar to the problem of flow past a forward facing step, where you basically are detachment reattachment zone and you form this circulating region there. And so by looking at the experiment, we thought, okay, that's what happens, that you have this fluid that's warmer, that it cannot penetrate up here, but after it passes this eddy that is forming at the separation zone, then you can transfer all the heat here. We weren't very happy though, because that's very hand waving. So what Eric did, went back home, University of Sydney, and used Daedalus, which is this fantastic model that finally is the first model that I know. What it does, not only it can calculate melt rate, which a lot of other DNS can do, but also it can change the shape of the ice given the melt rate. So you can actually really have a model that react to the melt rate and change the shape of the ice, which then will change the flow. So that's a very important step that it will, this is kind of a few years ago, like couple of 2 or 3 years ago, but that is a milestone also for understanding glacier melt and everything, because now we can deform the ice, which will then affect the flow field, and then we can understand the total process. So this is using Daedalus, is a DNS. And what we can see in these 3 pictures from his paper in PRF, that this is temperature, velocity, and vorticity. Let's look at these 2 first. That indeed, where the melting relative to the bottom of the initial iceberg location, the initial interface is higher. So this red line represents the melt rate. So it's higher in this point here and this point there is where those vortices are. So it's kind of what we said. So this water cannot get here, has to go around, and then this vorticity is able to bring ambient water, which is the white one, close to the ice surface, and that will melt more. So it's the location, this, let's think about it as like a half Fonkammer street, or like just a street of vortices that then affects the melt distribution underneath the base. And this is an almost diagram. So this is the length of the iceberg, and this is time. And in the red, basically the dark red is where it melts more. And overimposed in the gray is the location of the vortices. So you can totally see that those are the cause of the melting. So where there is a vortex, there is higher melting. So we explained a little dip. And if one goes a bit further, and then from the experiment, you calculate a geometrically average melt rate, that's the way Eric did it, where A is the area and V is the volume, then you can see that this average melt rate can be plotted versus the aspect ratio. And if the iceberg is very long, as we expected, because there is all that region where the melting is basically unaffected by these eddies on the front, then the melting approaches the value of the basal melt that we calculated with either Wicks and Campbell or Fitzmaurice and Al, depending on the velocity. But for very small aspect ratio, where that region where this notch exists, then you can have much more melting due to these eddies. So the aspect ratio, in the sense, that's what A affects. And also we can look at the change in sign of this aspect ratio, because we can foresee that if the aspect ratio is decreasing, then the side melting will be more important. Instead, if it's increasing, as the melting goes on, the base will be dominated. And you can calculate this change in sign, and it's when the aspect ratio is twice the ratio of the side melting versus the basal melting. So that means that even icebergs that have a high side melting velocity, if the aspect ratio is large enough, base melting is going to dominate. And that's what happened for tabular iceberg. Basically, tabular iceberg, because the aspect ratio is so large, they are just dominated by what happened underneath them. So let's have a look at this big iceberg and see if the Earth, because these are, now we're talking about 235 kilometers iceberg, as I told, one direction, so they can feel the Earth rotation. So another fun experiment we did that summer with another GFD fellow, Agostino Meroni, that we put, now we did an ice block, an iceberg, a cylindrical one. So it was that was much, the radius was much larger than the thickness of the ice. So simulating this large aspect ratio tabular iceberg, we put in the rotating table. And then what we did well, first we spin up the rotating table. Then we put the ice cube, the ice block, which is challenging by itself, right? Because again, we have to attach it, make sure it's flat and things. So that's why we couldn't get to very low Rossby number, because we couldn't spin up that tab too high. But we managed to do that. And then what we did, we increased the velocity of the table just to create, a velocity, what we call U tilde. That's basically delta omega times R, is this shear layer. The problem is that we start doing that, but then obviously this velocity spins down. So what we did for, we basically increased the velocity. We kept increasing it. So to keep basically this velocity profile fairly constant, say for 5 minutes. We couldn't do more than that, otherwise we spin up too much. But basically, we found a way to approximately have this profile of velocity maintained in the tank for a certain amount of time. So let's see what happened. So before doing that, what happened when you have a rotating, a flow going around an obstacle? We all know that from our GFD classes, you form this tail column. And so what we looked at that, you can look at formation of tail column when there is a uniform flow. That was done a long time ago. But more recently, now it's a while ago too, TED figured out also a solution when there is a shear flow. The dominant parameter in both cases is this alpha, that is the ratio of the Rossby radial deformation versus a non-dimensionalized draft, which we will non-dimensionalize with the total height of the water column at the iceberg location. When there is shear, there's another parameter that I think that called beta, but in our experiment, the beta is directly proportional to alpha, and so it wasn't changed independently, just because we want to learn one thing at a time. So what we see here in this plot is the difference between the upstream velocity field, well, actually between the solution of these two Taylor column problem and the upstream flow. Just to show that when you have a formation of Taylor columns, you can have an oscillate, which is not occupying the full width of the obstacle, because again, our Rossby number wasn't the smallest one you could, because of wasn't very small. I mean, was small, but not the smallest one you can get. You have an acceleration of the flow on one side and the formation of this Taylor column on the other one. So the lines are streamlines, and the color are this velocity difference. So basically what happens is when a Taylor column forms, what it does is deflect the fluid on the other side of the ice where it goes much faster. And there is this parameter alpha was worked by Herbert Upper, that if it's in a uniform flow with a uniform stratification for a cylinder, if it's above 0.5, then you have the formation, that's the critical value where you have the stagnation point, and then you start forming Taylor column for a uniform flow. Things are slightly changed when you have a shear flow. But basically, this green circle is the cylinder, is the obstacle, and you can see that you can form Taylor column on a lot part of that. And then when we look at the experiment down here on the right that Agostino did, indeed, in the melting, imprinted in the ice that we take out, you could see the Taylor column, at least. We could see actually because we put potassium permanganate in the water, so we know there was a Taylor column. But you can see also on the base of the iceberg where there is this region that is pretty smooth and not very melted. And then there are all these strikes where the melting, especially here, is much larger. So just qualitatively resemble this picture here on the right for larger alpha. And these values were taken, were calculated as solution for values of experiments, for lab values of experiments that we ran. Then when you actually quantify the melt rate, by again weighting the ice cube before and after, you can see that this is the usual old parameterization that goes to 0 when there is no velocity, that what you have is that below a certain threshold value, they're still melting. So now they're not, we don't think they're the plume before because the height is very small. But basically, if you have again, a tabular iceberg in a still fluid down here, what you have, you melt that water, it forms basically a gravity current underneath, and then it melts and then it goes up. So we call that this threshold is being, within this velocity is being melted by a gravity current. And here instead by this ambient velocity that is being accelerated when you have high rotation or low alpha value, or alpha less than 0.5. You have this gravity current forming, and you see, this Taylor column forming and enhanced velocity on the edge, and that causes the ice to melt much faster given the same velocity when you decrease alpha. So that's what Agostino found. Last things I want to show you just qualitatively, as I'm kind of finishing, is this is a movie that we've done during our cruise of a side of our iceberg. So if you look at it, all these scallops, that they're called scallops, they have size between 5 and 20 centimeters. They're everywhere. So my iceberg underwater, they're not smooth at all. They look very different from what we see them on top. Sometimes you see this when they flip, but they have this very beautiful shapes, and every time we look at an ice, it wasn't as smooth. So obviously having this kind of topography on the bottom will affect the plumes, will affect the drag coefficient if you want to parameterize that, will affect the flow, and studies are just starting to look at that. There was a very recent experiment in the lab using a huge tank, a corral, that observed scallops when the velocity of the ambient fluid was larger than 0.6 meters per second. However, in this study, because they were so big, they could only do an analysis on one scallop. So they couldn't really come up with a mechanism of why they form. Again, because they had to have such a big apparatus, PIV, they only focused 20 centimeters. That was the size of one scallop. Then some direct numerical simulation that were very recently done try to do similar things. This is again the same Daedalus program. Ice is blue. This is flow in this regime when there is Rayleigh-Bernard convections. You can see the formation of this channeling keels, but not scallops. And the reason is because they couldn't reach high enough Reynolds number. So the velocity was not high enough, didn't reach kind of this kind of threshold velocity. And so because again, DNS is very expensive, so they couldn't do in this study. But we're getting there to try and understand, now we have the observations, some lab experiments, some numerics. So hopefully in 5 more years, we'll understand this process as well. So this is just all the instrument. This bottom on the right is my little robot. They tethered with this yellow line that I put, it goes next to the ice. We survey iceberg with drone. This is a little jet yak that you see here that we sent near the ice because we couldn't go with the ship because, you saw what happened when you go near iceberg, they can fall down. And so there was this little remote control kayak that someone from the ship here was controlling. And so we took temperature, salinity, CDD profile and velocity profile at this distance with the ship, at this distance with with this jet yak. And you can see nicely here this foot of the iceberg. Other instrument that we had was multi-beam. You can reconstruct the bottom of the iceberg. And again, you sample it every week and you can measure melt rate. But those are very different measurements. So what do we know? What I think I can tell you that hopefully you assimilate during this talk. One is that iceberg is important because they represent half of the mass discharge from these ice sheets. Climate change is only going to make that actually total amount larger in time. So icebergs are going to affect our ocean, our distribution of property, nutrients, etc. The parameterization are good, even if empirical, but we cannot use just surface property, which is what most, if you think you have a climate model coupled with an ocean model, it's really hard to resolve the depth of your iceberg and the velocity and temperature profile. But we need to find a way to better come out with a temperature and velocity that is not just the surface velocity, because that doesn't cut it, basically. Ambient velocity is fundamental for the melting of this iceberg. And when there is not ambient velocity, we even have to consider these plumes because they do melt and they do contribute to the melting and actually to the distribution of the meltwater too. The aspect ratio is important, as we saw in those experiments of Eric, and especially when the melt rates are different at the base and the side, it can contribute to difference in melting. And rotation forms this Taylor column that can accelerate the ambient fluid on one side, so again, increase the melting. Although there is no melting on one part, the other one is much larger, that it produces an increase in melting. And these scallops, we need to learn how they form and how they affect the flow and the melt rate, possibly. What we don't know is it's still very difficult to take measurements on melt rate. Because there are so many errors, we take images, but even with a multi-beam for the underneath keel, you don't see everything. If there is another aspect of the iceberg that the beam cannot reach on the other side, they're very difficult measurements. And so hopefully satellite images and optical, from the top that we can see will be better. Maybe we'll have automatic iceberg detection, so we can have a lot of measurements, not just one every 5 years. But that is still how to measure melt rate is important, it's still challenging. And even more so, where does the water go? How does it affect the ocean? The transport of this fresh water has been basically not very studied. How this and how it affects the circulation, the ocean desertification, etc. So I'll leave you with a little movie that I took that summer, and then I'll take a question.
Thanks a lot, Claudia, for this talk.
Yeah.
So we're taking questions now. So whoever wants to ask the first question, go ahead.
Yeah.
Okay. So thank you so much, Dr. Claudia. This is Mohammed Al-Shafi from Helwan University in Cairo, and I would like to know how the location of the vortex street may be affected by these scallops you have shown at the end, and whether yes, you have said that we still don't have a good idea about the formation, but can we say that they are formed after the iceberg has formed, or are they a result of the maybe small vortices that affect the bottom of the iceberg, or the the ice mass?
So my understanding on scallop, which is limited, is that these are basically, they're formed by little vortices that are in the boundary layer. And there are some theory that did both a linear stability, a non-linear stability analysis, and linear, both of 2Ds and maybe 3Ds. There was another one. But I think this is a very different process than the one I show you in for that type, when there was the aspect ratio with the long iceberg.
Yes.
I think it's I think it's a bit different, because there what we found is if the iceberg was very long, then there was not any more texture.
Would form, yes.
Yeah, there were more next to the that basically the formation mechanism for those vortices was detachment and attachment. While here, I think it's just the turbulence given by the by the flow, and then it kind of organizes itself in this spacing. But because those are the kind of preferential, like this theoretical analysis did suggest that there was a preferential wavelength for this to form, for these vortices.
Okay. Okay. Yeah. Thank you so much for your answer.
Yes, hello. I would like to know what is the effect of the pycnocline when you introduce stratification on the drift of iceberg. And I was wondering, by listening to the work of Eric Esther, that you mentioned several times, he's an expert of the dead water effect, namely the fact that when you have solid body moving in stratified layers, you generate internal waves. And I was wondering if the basal melting could not be influenced by the wave breaking of internal waves. So is there any studies on the effect of dead water effect on the drift of iceberg, and especially in the basal melting?
No, not that I know, but someone else asked me this question, not Eric, someone else. I don't know if it was you, like a long time ago, but I never done a stratify. It's much, put it away.
Because the draft of the iceberg that you mentioned is very similar, for example, to the seasonal pycnocline. So as soon as the draft is of the order of the 6 zonal pycnocline depths, I suppose that the dead water effect will play a role.
They could, yeah. So this iceberg that I'm showing here in this slide, these were inside a fjord, and there is an interface between the top and the bottom, and there is a bit of stratification, but it's not very strong. You know, like we kind of simulate that more like a 2-layer. So there's not, you know, like I kind of see that the bottom one is pretty homogeneous, so that will not generate internal wave. But the big tabular iceberg that they flow into the ocean then depends on where they are. But I never looked into that, but I've been asked that question. It's just that doing this experiment, you know, think about a flume, and I kind of set it up to do 2 layers, and I think I don't even know if I can do it stratified, but maybe Eric can look at that particular problem with DNS. But I don't know. I've never.
Okay, thank you.
You're welcome.
Bye.
Chosan?
Thank you so much for the presentation. I was just wondering that the velocity underwater is mostly assumed that in a single direction. There might be any other chances the underwater velocity is streaming in different directions?
Okay, so in this study here that I showed, this was in a fjord. In a Greenland fjord that is pretty narrow, you know, like it was like 2 to 5 kilometers. And the flow that we observe is mainly along fjord. Mainly, you know, obviously there could be a storm, and, you know, if you go in the mouth, maybe there are eddies and things, but this is what we studied here was, what we observed was mainly along fjord direction, especially at depth. You know, on the surface, the wind might have some effect. Now for tabular icebergs, yeah, depends on where they are and when they drift. If there is a region around Antarctica and, you know, around there that has that would change, that will be kind of a more complicated problem, but you can do just a 3D problem, because you just have to sum the vector again, integrate it in depth, and then you'll find the final direction of propagation of the iceberg. It's not any hard, you know, it's a bit harder, but it's still the same principle that you integrate the depth, including the direction at that point, and then you'll find the average, both magnitude of the vector and the location, you know, of the vector. So I don't think it will change anything in terms of how you approach it.
Okay, thank you.
Ted Johnson.
Hi, Ted.
Hi, Claudia. It was a great talk. Thank you.
Thank you.
I was fascinated that you thought Coriolis effects could be important. How small would you estimate this Rossby number to be for your real life tabular Antarctic?
Yeah, I wrote it here actually.
Oh yeah, okay.
Yeah, so the alpha will be 0.1 with these values of, you know, if you have a 20 kilometers, I'd say, you know, you have to make some choices, but we look at it. And so if you make these choices of velocity and everything, you know, like it could be important, you know, like you get a pretty low value of alpha. Sorry, I didn't calculate Rossby number just because it was the ratio that's important. So we do think that is fairly important. Actually, there's some, when Agostino was doing this experiment, Anna Fitzmaurice, that she did the other experiment, she was doing a numerical study with Stern. So there is a Fitzmaurice and Stern paper that actually looks, she's done a numerical simulation, you know, with you know, just one iceberg there, and she observed turtle column on the bottom too, and the formation and everything. So it's very similar, even using a more like GCM model with kind of realistic scale and F and everything. So these big ones, yeah, we expect to be influenced by rotation, even in both the trajectory, obviously, and the melting.
Could you put those references or just send them at some stage?
Yes.
Sometime in the future.
Yeah, no, they start. Yeah, actually, you know what? This is a little thing. I'm going to send, because I just finished to write an annual review of fluid mechanics about this. That's why I'm talking about that, because, you know, I kind of did a lot of work for that. And I said, okay, I'm going to tell you what I think. So I can send you a you know, like whatever. It's been you know,
Great,
still
thank you.
the reviewer is doing, but there are all the references there too. So I'll do that.
Thanks very much.
Yeah, there's a comment in the chat, and I totally agree. That group that developed Daedalus and found how to do this, there, you know, when they were here that summer, both Eric and his supervisor, Jeff Ballis, and I said to them, guys, you have to figure it out. We have to move this ice, otherwise, you know, we can compare apple with the lab and everything. And they went home and with that big group did it. It's just fantastic, I think.
Yeah, so I had a question about that XT diagram that you showed and argued that larger vortices cause more melting, maybe 2 slides before this. So
this one?
No, actually, like the one with the XT diagram, which showed this rays. Yeah, that one.
Mm-hmm.
So the vortices downstream the block, they are actually being convected, so they travel. They don't basically stay somewhere to kind of facilitate that heat transfer. But the question is, so yeah, you could say that they grow, and the larger they are, the more, you know, heat they transfer. But why it doesn't extend to the trailing edge? Why you have those 2 peaks, and then it doesn't actually, it tails off almost, like it doesn't extend to the downstream of the block.
Okay, so first of all, these are numerical simulation, right? And they're awesome, but they're still numerical simulation. And I'm just thinking, I wish Eric or someone else was here. I'm just wondering if these were 2Ds. I don't remember actually, but because the vortices are so big, I'm guessing they're 2Ds, hence they don't break out. Because if you see the experiment here, I show you this. So you do see the eddies, right? But then, and they're more, you know, they're more here, but then they're kind of mixed, you know, then they kind of form a normal boundary layer after. So they get all kind of destroyed, you know, because you have the attachment zone and then you have the first one and second, but you know, you have to think that it's not that the real flow is much more turbulent. And again, I can identify some eddies here. And as you said, they travel down, but I think the strength is higher here and they're more coherent. And so that's where they kind of carry a lot. Downstream, then they kind of get all mixed up. So they don't have, they're probably smaller and they cannot have such a intense. Now, if we go back to the numerical, I'm guessing that if this iceberg was a bit longer, there might have been a 3rd eddy here and so on. But I think, you know, these were really the first things that Eric did a few years ago with this code. So I think we need to, again, push the Reynolds number a bit higher. But again, with a DNS, you can do one thing, but not the other. So that's my speculation, but I don't know. I know that in the lab, I didn't observe any advancement at the end, but so that's my speculation that you have a bit more coherent vortices near the detachment reattachment zone, and in the back they get kind of broken off and be part of the normal turbulent boundary layer.
Yeah, thank you.
Again, but this is a speculation.
Yeah, this is just a snapshot in time. Those vortices do advect to the right.
Yeah. But as I said, I will. But it's very. This is again is a relatively low Reynolds number, and it might be even be 2D. So I believe the process, but not necessarily the exact location. In fact, if you want, in the lab, we didn't observe 2 peaks, we only observed 1 and things. So, but you know, this is a major breakthrough in trying to simulate this. And so.
Okay. We've got a last question on the chat, which is the roughness observed at the surface seems to have kind of a hexagonal shape. Any comment on that? The beehive.
Yeah. I don't know. I mean, they're called scallops. So actually, more than I don't know if it's a scallop is a shell. So but this video that I saw, they actually are very interesting because they are a bit more less smooth. I agree. And also was very interesting that the bottom, sometimes they had sediments, I think, inside, so you could see better. But I don't know. They have a bit different shape that I've seen before, and I don't know why. But I don't know if you really can distinguish between a scallop and an hexagon at this point. It might be that is an early formation and then it gets smoothed up to something else, or I don't know. But the reason why they are oriented they're always oriented in the direction of the flow.
Okay, I think that's all we have time for. Some people comment that it has a similar
to
structure to Rayleigh Benar cells.
That's interesting. It's vertical. So those were vertical walls. So it's a bit hard to think.
We had a comment from Grey Worcester, but I couldn't hear it.
Oh, you know us, actually.
Yeah, so Grey Worcester says nature loves hexagons.
Good, good.